Right now, as you watch this, time is moving faster for you than it is for someone standing at sea level. Not metaphorically, not theoretically, literally. Every second you experience passes differently than it does for billions of other people on this planet. Your future arrives at a different rate than theirs. And the difference isn't small. It's measurable, quantifiable, and absolutely real. In 2010, physicists at the National Institute of Standards and Technology measured time dilation between two atomic clocks separated by just 33 centimeters, about the length of a ruler. One clock was elevated slightly higher than the other. After running for weeks, the higher clock had aged measurably more than the lower one. 33 centimeters, 13 inches. That's all it took to prove that time itself bends under the weight of matter. But here's what should terrify and fascinate you in equal measure. This isn't some quantum quirk happening at the edge of reality. This force is stealing time from entire civilizations. It's stretching and compressing the fabric of existence across the cosmos. And in the most extreme corners of the universe, it's creating pockets where time nearly stops. Regions where millions of years pass in the universe beyond, while mere moments tick by inside. What if I told you that gravity isn't just pulling on objects, it's pulling on time itself? That massive objects don't just curve space, but drain the flow of time like whirlpools drain water. Today, we journey through evidence that challenges everything we thought we knew about the passage of time, the nature of gravity, and what it means to experience reality. Prepare yourselves. We begin.
In 1907, Albert Einstein was 28 years old, working as a patent clerk in Bern, Switzerland. He had already published his special theory of relativity 2 years earlier, upending physics with the revelation that space and time are interconnected, that simultaneity is relative, and that nothing can travel faster than light. But something troubled him. His special theory only worked for observers moving at constant velocities, inertial reference frames. It said nothing about acceleration or gravity. And gravity was everywhere, fundamental to the cosmos, holding planets in their orbits and shaping the structure of galaxies. Then, on what Einstein would later call the happiest thought of my life, he experienced an insight that would change everything. He imagined a man falling freely from the roof of a house. Picture it, the moment the man steps off, before fear sets in that instant of pure free fall. In that moment, Einstein realized, the man wouldn't feel his own weight. He would be weightless. His stomach would drop just as it does on a falling elevator or a roller coaster plunge. And if he released objects from his pockets, keys, coins, a watch, they would float beside him, motionless relative to his body. To the falling man, those objects would be indistinguishable from floating in the depths of space, far from any gravitational field. The man couldn't tell if he was falling in Earth's gravity or drifting in the void between stars. This simple thought experiment led Einstein to a principle so radical it would become the foundation of general relativity. Gravity and acceleration are fundamentally equivalent. There is no experiment you can perform inside a closed room that can distinguish between being stationary in a gravitational field and being accelerated at a constant rate in empty space. But if gravity and acceleration are equivalent, and special relativity already told us that acceleration affects time, then gravity must affect time too. The mathematics led Einstein to an impossible-sounding prediction. Time, he concluded, must run slower in a gravitational field than it does far away from massive objects. A clock on the ground floor of a building would tick more slowly than an identical clock on the top floor. The difference would be minuscule. For a typical building, mere billionths of a second per day, but it would be real. His colleagues were skeptical. Some were openly dismissive. Time was time, the universal metronome by which all events marched forward in lockstep. the absolute backdrop against which the universe's drama unfolded. How could gravity, a force that pulled on objects, somehow pull on time itself? It was absurd, mystical even. But Einstein's equations were unambiguous. They emerged naturally from the mathematics, an unavoidable consequence of treating gravity as the curvature of space-time rather than as a force. The equations predicted that on the surface of the Sun, where gravity is 28 times stronger than on Earth, time should run approximately 66 parts per million slower than it does in empty space. For every million seconds that pass far from the Sun, about 11.5 days, only 999,934 seconds pass on its surface. The Sun was aging slower than the universe around it. Every second, it lost 2/millionths of a second relative to distant space. Over billions of years, these stolen moments would accumulate into lost millennia. Einstein knew this prediction was testable. Light itself would be the messenger. For decades, Einstein's prediction remained just that, a prediction. The differences were too small to measure with existing technology. Mechanical clocks weren't accurate enough. Even the best pendulum clocks of the early 20th century gained or lost seconds per day due to temperature changes, mechanical imperfections, and vibrations. How could you measure time dilation effects 1,000,000 times smaller? But Einstein knew where to look for proof. Light itself would carry the signature of time dilation.
A 22-meter tower on Earth barely scratches the surface of what gravity can do to time. Earth's surface gravity, 9.8 meters per second squared, creates time dilation of only 0.7 parts per trillion. To see the full, reality-warping effects of time dilation, we needed to look beyond our planet. We needed something far more massive than Earth, generating gravitational fields millions of times stronger. We needed the Sun. Throughout the 1960s and 70s, astronomers began measuring the spectral lines of light coming from the Sun's surface with unprecedented precision. These spectral lines, the unique fingerprints of elements like hydrogen, helium, calcium, and iron, appear as dark absorption lines in the Sun's spectrum, created when atoms in the solar atmosphere absorb specific wavelengths of light. Scientists knew what wavelengths these lines should have. They could measure them precisely in Earth-based laboratories. But when they measured the same lines in sunlight, something was wrong. The lines were shifted, moved toward the red end of the spectrum. The shift was tiny, about 2 parts in a million, but it was real, measurable, and consistent across all spectral lines. This was gravitational redshift on a cosmic scale. The light climbing out of the Sun's gravitational well was losing energy, its frequency decreasing as it escaped. And because frequency is directly related to how fast time runs, this meant time on the Sun's surface runs slower than time on Earth. The measurements matched Einstein's predictions almost exactly. Time on the Sun's surface runs about 66 millionths of a percent slower than time on Earth. It seems insignificant. A clock on the Sun would lose only about 60 seconds per year compared to an Earth clock. But consider, the Sun is 4.6 billion years old. Those missing millionths add up. If you could somehow have placed a clock on the Sun's surface when it formed, and another clock in deep space, far from any gravitational influence, and if both clocks had survived until today, the Sun's clock would now be roughly 3,000 years behind. 3 millennia have been lost to the Sun's gravitational well, stolen second by second across eons. Think about what that means. The Sun hasn't experienced as much time as the universe around it. From the Sun's perspective, it's younger than 4.6 billion years. The universe has aged more than the Sun has. But the Sun is nothing compared to what lurks elsewhere in the cosmos. White dwarfs, the collapsed cores of dead stars, pack a sun's worth of mass into something the size of Earth. That density increases surface gravity by a factor of about 100,000. Time dilation increases proportionally. On a typical white dwarf, time runs about 300 parts per million slower than in distant space, about 0.03% slower. A clock there would lose 26 seconds per day. Neutron stars compress even more mass into spheres just 20 kilometers across. Surface gravity reaches 200 billion times Earth's gravity. Time dilation becomes dramatic, often 20–30% or more. A clock on a neutron star surface might lose 20 minutes per hour compared to a distant observer. Spend what feels like 1 hour on a neutron star, and 75 or 80 minutes pass for everyone else. And at the extreme edge of possibility lie black holes, where gravity becomes so intense that time dilation approaches infinity at the event horizon. Time doesn't just slow near a black hole, it can slow by factors of thousands or millions. Close enough to the event horizon, 1 second for you could equal years, centuries, or millennia for distant observers. These objects don't just slow time, they torture it, stretch it, compress it into forms that defy human intuition. They create regions of space where cause and effect become tangled, where the sequence of events depends on where you're standing, where the very concept of now breaks down completely. In 1971, physicist Kip Thorne at Caltech calculated what would happen to time near a rapidly rotating black hole, a Kerr black hole. His equations showed that in the ergosphere, the region just outside the event horizon, space and time become so twisted that time partially becomes space and space partially becomes time. The distinction between them blurs. You could no longer stand still. Space-time itself would drag you around the black hole, forcing you to move through what we'd normally consider time as if you were moving through space. But the evidence forces us to confront an uncomfortable possibility. Time dilation isn't just an exotic phenomenon affecting distant stars and black holes. It's affecting you right now in ways you've never imagined. It's embedded in technology you use every day. It's shaping your experience of reality at every moment. And we're only beginning to understand what that means.
On September 14, 2015, at 09:50:45 UTC, both LIGO detectors, one in Louisiana, one in Washington state, detected a distinctive signal, a chirp, a brief increase in frequency and amplitude lasting just 0.2 seconds. The signal came from two black holes colliding 1.3 billion light-years away. The black holes, 29 and 36 solar masses, had been spiraling into each other for millions of years, gradually losing energy to gravitational waves. In the final moments, they orbited each other hundreds of times per second before merging into a single black hole. The detection, designated GW150914, was the first direct observation of gravitational waves, confirming a century-old prediction by Einstein. But hidden in the data was something even more profound, evidence of mutual time dilation between the black holes themselves. In the final moments before merger, these black holes were experiencing such extreme mutual gravitational fields that time dilation between different parts of the system became significant. Each black hole existed in the other's gravitational well, meaning time ran slower for each one from the other's perspective. Think about what this means. From the perspective of black hole A, black hole B's time was running slower. From B's perspective, A's time was running slower. They were both right, and the orbital dynamics had to account for this mutual time dilation. The gravitational waves themselves, ripples in space-time spreading at light speed, carried signatures of this mutual time dilation encoded in their frequency patterns. The chirp wasn't just a simple increase in frequency.
It was modulated by relativistic effects, by the time dilation each black hole experienced in the other's field. By analyzing the wave characteristics in exquisite detail, physicists could reconstruct not just the masses and spins of the black holes, but the time dilation effects they experienced in their final dance. The data revealed that in the last few orbits, time dilation between the black holes exceeded 20%. Each was aging 20% slower than it would have in isolation. But the implications go even deeper. In 2017, LIGO detected another black hole merger, GW 170814. This one observed by 3 detectors, both LIGOs and the Virgo detector in Italy. With 3 detectors, scientists could triangulate the source position and analyze the gravitational waves from multiple angles. The data revealed something unexpected. Gravitational waves themselves experience time dilation as they propagate through space. When gravitational waves pass through regions of space with significant mass density, galaxy clusters, for instance, they slow down slightly. Not because they travel slower than light, they propagate at exactly light speed, but because time itself runs slower in those regions. This means gravitational waves from distant sources carry information about all the mass they've passed through on their journey to Earth. By analyzing subtle timing variations in gravitational wave signals, astronomers hope to map the mass distribution of the universe in an entirely new way by measuring time dilation along different sight lines. The implications are staggering. In the vicinity of merging black holes, time doesn't just slow, it becomes spatially variable. Time runs at different rates in different locations, just meters apart. The very concept of simultaneous events breaks down. Now becomes a meaningless concept, undefined, impossible to specify.
For more space and informational content, subscribe.